thanks to everyone. Thanks, Henry, particularly for having us here. So I'm going to talk about the Marino-Welsh conjecture for series parallel graphs. It's also the talk that I'll give tomorrow at the Polynomial Conference. So, James, you can ignore one of the talks. So, who are these people? There's Marino, and there's Dominic Welch. They're the people who made the conjecture in the first place. This is Steve Noble, who's my collaborator, who has many interests, as you can see there.
What is it? It doesn't even look like it. What is it? What's he done his hair?
Oh, he's pretending to be Elvis. He's at karaoke night or something. I have to go fast because I've got slightly too many slides for half an hour. So, okay, so what are we talking about? We're talking about a graph, and we're talking about three parameters, which are the number of spanning trees, the number of acyclic orientations, the number of totally cyclic orientations, and Marino and Welsh conjectured on a small amount of evidence that the number of spanning trees is always dominated by either the number of acyclic orientations or the number of totally cyclic orientations. I'll tell you what those are in a second. Trying to do induction with a max is very difficult, so you can rephrase the conjecture to get something that's similar in spirit, if not identical, and then you want it to be twice the number of spanning trees should be less than the sum of the two things, or you can express it multiplicatively, and in this case you want the number of spanning trees squared to be less than the product of the other two parameters. Bridgeless and loopless is needed because one of the alpha or alpha star will be 0 if there's a bridge or a loop, respectively. Oops, wrong button. Of course, you guys all know what bridges and loops are.
Go on, just explain about that. So those conjectures are equivalent,
Not precisely.
No, okay.
Not precisely. We all know what spanning trees are, so a set of edges that touches every vertex and contains no cycles. Our favourite graph has got 2,000 of those. An orientation, then, is just an assignment of a direction to each edge. I mean, if there are E edges, then there are 2 to the E different orientations. Okay, we're going to extract some of those orientations and talk about the numbers of those things. So, an orientation is acyclic if the graph with the directions has no directed cycles. So you can't make a cycle following the arrows. And it's totally cyclic if it has a directed cycle through every edge. So no directed cycles or directed cycles everywhere. They're the two extremes.
So the totally is like some sort of Hamiltonian type directed cycle, is it?
No, it just has to have a directed cycle anywhere.
For each edge, there exists a directed cycle contained.
Yeah.
Oh, okay.
Yeah. Every edge lies in some directed cycle in that orientation.
Okay.
And obviously for the Peterson graph, all the conjectures hold, because you can see the number of spanning trees is small. It's actually the number of totally cyclic orientations is even smaller, but that's compensated for by having shed loads of acyclic orientations. Okay. You can have equality, and here's the graph that gives equality in all three versions of the conjecture. The diagon, there are 2 spanning trees that I've exhibited there. There are 2 acyclic orientations, either direct both edges from left to right or right to left, and 2 totally cyclic orientations when you direct the edges in opposite directions or the other way. So, tau is 2, alpha is 2, alpha star is 2, and that sort of establishes the base situation. If the graph is plane, then any orientation of the graph can be associated with an orientation of the dual graph. All I'm going to do is take any directed edge, and I'm just going to turn it clockwise, anti-clockwise. So, and then that will just give you a correspondence, one-to-one correspondence between the orientations of the graph and the dual graph. So there we are. I turn that one left to right, and I'm going to do the same with all of them, and now I've got an oriented dual graph. A few minutes thought will convince you that an edge E does lie in a directed cycle, if and only if it does not lie in a directed cycle in G star. So these parameters are actually just dual parameters to each other. So if the graph's got alpha totally cyclic orientations, then its dual graph will have alpha acyclic orientations.
Isn't there a more general conjecture about the tuple polynomial evaluated at 2 points in the plane?
Yeah.
And that's a special case of it, isn't it?
Yeah.
Yeah.
Yeah. So,
sorry, are these parameters preserved under Whitney switching?
well, they're all evaluations of the tuple polynomial.
So yes?
So yes. So anything that preserves the matroid structure will preserve all of these numbers. So, okay. And we all know that the number of spanning trees in a graph and a dual are the same. So. Okay, so in fact, all three parameters are just evaluations of the tuple polynomial at specific xy pair in the tuple plane, if you like. Number of spanning trees is the tuple polynomial evaluated at 1, 1. Number of acyclic orientations is the tuple polynomial evaluated at 2, 0. And the number of totally cyclic is tuple polynomial evaluated at 0, 2. So we can't really talk about acyclic orientations or cyclic orientations of a matroid because we don't know what it means. It doesn't have any meaning. But we can certainly evaluate the tuple polynomial at those points. So, so we can make the conjecture into a matroid conjecture just by saying that we want the tuple polynomial at 1, 1 to be less than or equal to the maximum of the tuple polynomial evaluated at 2, 0 times and the tuple polynomial evaluated at 0, 2. And we can just do the same thing for the multiplicative version of the conjecture or the additive version of the conjecture, and all will still be open. Yeah.
Well, just a very quick question: is there a known combinatorial interpretation of those things for, say, binary matrix?
I don't know one, and I've looked. Yeah. So, but I mean, probably James knows that for a regular matroid they count something, sensible. So here we are in the tuple plane, and what we're really saying is that if you look at this line segment in the tuple plane, then as you go from here to here, this tau should be lower than one of the two values. You can imagine evaluating a function at every point along this line, and you want that function to have tau to be less than either of the two endpoints. Okay, so we can then just turn that into a continuous version of the conjecture where we ask that if we do evaluate the tuple polynomial from the point 0, 2 to the point 2, 0 in a straight line, then the values that you get should form a convex function. So here's the one for the Peterson graph. Here's the number of the ones that there were 19,000 of, or whatever. Here's the number of ones where there are only 1920, and here's the number of spanning trees.
That's a strictly stronger conjecture, though, right?
Correct. That's strictly stronger. So it's convex throughout that whole region. Is that clear what this graph is?
Convex and something with the derivatives at the end, don't you?
Yes. Yeah, no, I mean, it won't do that though, because it's polynomial and continuous and, Okay. So people whose names I don't know how to say, except for Marino and Noble, proved that the conjecture is true for all paving matroids. And in fact, they proved something stronger. They proved that if you take any line in the tuple plane parallel to the one that I just showed, and in the top, the first quadrant, then it will be convex along that line. So, and of course we all know that paving matroids are, that almost all matroids are paving matroids, and so they've done almost all of the problem. So, but
they also have very simple tuple polynomials, right?
yes.
It only depends on the number. It only depends on the number of circuit hyperplanes.
That's right. So basically what you can say is they've done all the low-hanging fruit, and they've left the case people are interested in, graphs, unsolved. So,
Down at the cherry at the very top of the tree.
that's right. That's right.
If you strengthen the full conjecture to make a statement about all parallel lines, is that not known to be false?
That's not known to be false. It's known to be true for if you go from 4, 0 to 0, 4, but I didn't have time to put it in the slides. And yesterday I suddenly thought, oh, I should really find a graph where it's false for, you know, x plus y equals a half or something like that. But I couldn't find one in 10 minutes. So. That's a good question. Okay. So what's known for graphs? Well, if a graph is sparse, like not many edges, then you throw down your orientations and most of them will not create cycles. Many of them will not create cycles. So it tends to have lots of acyclic orientations. If the graph is very dense, then you create lots of cycles, pretty much however you throw down the orientation, until you get lots of totally cyclic orientations. Carsten Johnson showed that if you were sparse enough, then, so he quantified this sort of general thought. If you're really quite sparse, then the number of spanning trees is going to be less than the number of acyclic orientations. But, I mean, what are the graphs with 16n over 15 edges? What do they look like? It's like one cycle and an edge or something like that, you know. And he also showed that if G is bridgeless with n vertices where n is really quite large, n's the number of edges, then you get lots of totally cyclic orientations. So he's done the case where you've got almost no edges and you've got tons of edges.
Oh, I don't know, tons of edges. I think because the number of edges you'd expect to be about squared, and so it's still only order n.
So is it, yeah.
I don't think you should expect the number of edges to be higher. I think you should expect the number of edges to be about 2n.
For a counterexample.
Well, Thompson asked if his bounds could be pushed. So he asked whether you could push the number of edges where where the number of acyclic orientations dominates, right up to 2 times n minus 2. And the number of the graphs with many totally cyclic orientations down to be true for all graphs with at least 2n minus 2 edges. Okay, so he's essentially trying to say this is not a conjecture about the relationship between alpha and alpha star. This is 2 conjectures about the number of spanning trees compared to in sparse graphs and the number of spanning trees in. Okay. Now, why 2n minus 2? Well, now we're at the midway point for duality, right? So if you've got, so if something, you know, if it satisfies this, then its dual will satisfy this. And so really 2n minus 2 is the sort of cutoff point. You're never going to be able to push it beyond 2n minus 2 or below 2n minus 2. Still possibly could push it to exactly 2n minus 2, but maybe not. So really these are just equivalent conjectures, and if you're a graph theorist and you don't like duality, then you speak to a Matroid theorist and move to co-graphic matroids. Okay. Now, Leontief is false. His question is false. Here's a nice graph. It's got n minus 2 diagonals, 2 edges, and exactly 2n minus 2 edges. And these are the computed numbers of spanning trees, acyclic orientations, and totally cyclic orientations. And you plug in the numbers and you discover that, in fact, when n is at least 6, then tau is higher than alpha. But we're still at that point. So Carsten's approach can't work because you will not get to a point where tau dominates, where alpha dominates tau. And dually, you can't do it the other way either. Okay. So, Paving Matroids are a huge class of very uninteresting Matroids. Series parallel graphs are a tiny class of interesting graphs, hopefully. We need to do this messing around with two-terminal series parallel graphs. So, a two-terminal graph then has got two distinguished vertices called the source and the sink, S and T. You take two-terminal graphs and you can put them together in series by putting the sink, identifying the sink of one with the source of the other. And the parallel connection is when you identify the two sinks and identify the two sources. Okay, and then a series parallel graph is anything you can get by starting with K2 and then doing that as many times as you want. So you're constructing the graph. You start with K2, that's in your bag. Well, now you can put K2, series K2, now you've got a little path in your bag. Well, now you can put that path with an edge of K2 in parallel with it, and now you've got a 3-cycle, and so on. So any two-terminal series parallel graph can be constructed by all these series and parallel operations, and if you care about it, you can keep track of how you did it by using a tree. So these are two leaves, which are K2s, and this means put them in series. That corresponds to that part of that graph. But you don't need to know too much, except for how you build the series parallel graphs from small ones. Okay, so our main result then is that the multiplicative version of the conjecture is true for series parallel graphs. It just says that.
So for this conjecture, they're not equivalent. Is the one stronger than the others, or they're not comparable?
Yes, I haven't really worked it through. Some are stronger than others. I mean, but yeah.
The comparison of the geometric and arithmetic means.
Yeah,
Yeah,
that's
no.
right. Yeah,
Say that again, Jack.
It's a comparison of the geometric and arithmetic means.
yeah, that's right.
Yeah, the multiplicative version is the strongest.
So okay, so that's yeah, okay. Okay. Anyway, it's pretty small sort of family of graphs, but it doesn't work by showing that either alpha or alpha star dominates. So it doesn't use the approach that can't possibly finish the problem. And series parallel graphs, you have lots of graphs around the critical point where they're sort of self-dual in terms of numbers, or actually self-dual. So it's sort of the hard part of the element range, but we've had to trade off graphs for series parallel graphs. Okay, so what we're going to do is we're going to build a machine, an algorithm that produces a minimal counterexample. Then we're going to run that algorithm, and then we're going to say it failed, and therefore there is no minimal counterexample. Okay? Okay, so what we're going to do is, minimal counterexample is two connected. So its final operation must have been parallel connection of two things. Because that's the only way you can get a two connected series parallel graph. We're going to define a concept of reducibility, which says that if this is a counterexample, then there must be a smaller counterexample. And then we're going to classify the irreducible graphs and say, these are irreducible, these are the only candidates for being a minimal counterexample, but none of them are a minimal counterexample, so we don't. Now, series parallel graphs are nice because as you build them up, you can often combine the information about the structure of the two parts to get information about the structure of the whole. In particular, you can find the number of spanning trees of the series connection of two graphs, because a spanning tree of the series connection must be a spanning tree in the first part and a spanning tree in the second part. So it's just multiplicative. But it's not multiplicative on parallel connection. So, but it turns out that we can keep track of additional information. So now we're going to keep track of 6 parameters instead of 3. And the 6 parameters of the two smaller graphs are enough to give you the 6 parameters of the series and parallel connections. What are these extra things that we're going to keep track of? These are two forests. A set of edges that induces a two-component forest with S and T in different components. Now, why is that useful? Well, that's useful because if you have a parallel connection of two things, you have a spanning tree in one half and a two forest in the other half, then that whole thing is a spanning tree of the parallel connection. Okay. I mean, the whole problem that we can't just say spanning tree here, is that the two spanning trees both connect S to T and therefore would create a cycle and no longer be a spanning tree. Then we've got some variations. So a very acyclic orientation is one that not only has no cycles, but also has no directed path between S and T in either direction. And an almost totally cyclic orientation is an orientation in which every edge is either in a directed cycle or does lie on a directed path between S and T. And I'll call those tau 2, alpha 2, and alpha 2 star. Right. Then you sit down for a while and you get some equations, and they're actually very easy to say. So the exact nature of these doesn't matter. All they are to indicate is that if you know tau and tau 2 of your two component graphs, then you know tau and tau 2 of your parallel connection. Okay. So 6 parameters that we can keep track of. Right. Now this is the key thing. A graph is reducible if there is sorry, I changed this slide this morning and then forgot to actually make it right. A graph is reducible if there exists a smaller graph H such that for all graphs K, if H parallel connection K is okay, in other words satisfies the conjecture, then G parallel K is also okay. So what that says is whenever you see G parallel anything, you can just replace G with H parallel anything, and you've got a smaller graph that's still okay. The property is that whenever you replace G by H, things get better. Things don't get worse.
Is H in any way related to G? Or
No.
Can it be any small?
It can be any graph. You just have to find any old graph such that, well, we'll see how it works. It's pretty, yeah, anyway. The point is, a minimal counterexample can't use G in this situation. And when I say use G, I mean at any stage in the construction process, as soon as you see G, you can stop because you could always just have replaced it with H at that point and everything would be better. Right. How on earth are we going to show that something is true for all graphs K? Well, this is how we're going to do it. K is some graph, arbitrary graph. It has some parameters, tau 1, tau 2, alpha 1, alpha 2, alpha star, no, sorry. It has some parameters. T1 and T2 are the tau 1 and tau 2 for K. The number of spanning trees of G in parallel with K is just a linear combination of T1 and T2 that uses things that depend on G. If I put H in there, then it's just going to be the same linear combination, but these numbers will now be things that will now be tau of H and tau 2 of H. So these numbers, T1, alpha 1, A1, C1, T2, A2, C2, just depend on K. So fixed, K, unknown but fixed. There are some parameters that come with K. If we parallel connect it with G, we'll get this particular linear combination of things. If we parallel connect it with H, we're going to get a different linear combination of the same things. An example is needed, isn't it? What I'm going to claim is that if ever you see this graph, you can stop and replace it with this graph. Because if anything involving this graph is a counterexample, then anything involving this other graph will also be a counterexample. Okay. These are the 6 parameters for G. 20, 25, 62, 36, 36, 18. These are the 6 parameters for H. 4, 4, 4, 2, 14, 4. Okay. Now we're going to compare what happens when we take H, parallel connection with something unknown, and what happens when we take G, parallel connection with something unknown. So what I'm claiming is that G is reducible, and H is the witness that shows that it's reducible. H is the guy that you can put in instead of G. Okay. Well, if H, parallel connection K, is okay, then for these numbers, all determined by K, we have the number of spanning trees of H, parallel connection K, which is 4T1 plus 4T2. So the two 4s come from the graph H, and the T1 and the T2 come from K, which we don't know. This is the number of acyclic orientations of H parallel K, and this is the number of totally cyclic orientations of H parallel K. Okay. We know that H parallel K is okay. It satisfies the conjecture, and therefore this equation is satisfied, even though we don't know what T1, T2, A1, A2, and so on are. What would happen if we replaced H with G? So now we're looking at G parallel K. Well, the number of spanning trees would no longer be 4T1 plus 4T2 squared. It would instead be 20T1 plus 25T2 squared. Because these were the T1 and T2 values for H, and these are the T1 and T2 values for G. So this number, the number of spanning trees, has increased. Okay? When we put G in there, you get more spanning trees than if you had H in there, because G is a bigger graph. But how much is it increased by? Well, if you multiply this by 25 over 4, you'll get something strictly bigger than this. And so the left-hand side has increased by, at most, 25 over 4 squared. What about the number of acyclic orientations? Well, this is the expression when H is in the hot seat. This is the expression when G is in the hot seat. So this value has increased by a factor of at least 62 over 4. And this is increased by a factor of at least 36 over 14. So that means that if this expression held in H parallel K, then it must also hold in G parallel K, because this has been increased by at most 25 over 4 squared, this has been increased by at least this number, and this number is bigger than this number. So the inequality that showed that H was okay is now even better, showing that G is okay. So that didn't depend on the actual identity of K at all. K could have been anything at all. All you're using is that H is okay, so this holds. If you replace H by G, then you get an inequality that's even stronger than it was before. Okay, so that's reducibility. In practice, what that means is that as we're constructing series parallel graphs in a systematic way, as soon as we encounter something that is reducible, we can just stop there. There's no point in exploring that part of the tree any further, because you'll never find a minimal counterexample in that part of the tree, because any time you see a G anywhere in that construction, you can replace it with an H and have a better counterexample. Okay, so here's an algorithm. We're going to find a minimal counterexample by systematically building series parallel graphs. Start with K2, that's got one edge. All we've got in the bag is K2. We do K2 series K2, put that in the bag. K2 parallel K2, put that in the bag. At each stage, we take two graphs from the list, the two graphs with the total sum of edges being as little as possible. Then we check whether they're reducible by checking whether they can be replaced by any of the smaller graphs already on the list. So for each of the small graphs, we say, can we show that we can replace H by this small graph? Can we show that we can replace it by this small graph? If we can't prove it reducible, we add it to the list. If we can prove it's reducible, we stop. We throw it away. We no longer pursue that avenue. We avoid creating any series of parallel classes of size more than 3. That's because you can show that a minimal counterexample cannot have that. So we don't need to worry about those. Okay. So every graph not on the list is reducible. So we just have to somehow characterize all the graphs on this list, and we're done. They're the only candidates for minimal counterexample. Well, so then you program it, and you start running, and it terminates. So this is a finite process. It doesn't, I mean, before you do it, there's no reason to think it will terminate. You might just keep building things and they're not reducible and so on and so forth, but in fact it does terminate. It terminates with only about 20 graphs on at most 7 edges. So summary, let G be a minimal counterexample. Then it must be the parallel connection of two things, because it's two connected. Each of these things must be irreducible, because if they were reducible, we wouldn't have constructed them. We would have said, this is reducible, not a valid place to find a minimal counterexample, let's stop. Well, that means that G1 and G2 must be on the list, because everything that's irreducible is on the list. The only things that are not on the list are things that are reducible, because they lie beyond in the search tree, they lie beyond something that you could never find in a minimal counterexample. But then you just look at the list of graphs, small number of tiny graphs, and they all satisfy the conjecture. So, conclusion, conjecture is true for series parallel graphs. When I first wrote this slide, I wrote, proof has no chance of generalizing because it so heavily involves series parallel graphs. But someone coming to the Tut Polynomial Conference is a student from Denmark who has generalized it to tree width 3. So I think I'll have to change that. But obviously, I mean, just going from series parallel to tree width 3, maybe that's not so, I mean, that's not going to resolve it ultimately, is it? So, new ideas are needed, especially around the sort of self-dual point. And we looked quite hard for some other examples where Carsten's sort of hope was dashed. Like, we've only got these examples where right on the exact, exactly half the number of edges, half the ranked number of edges. I mean, you know what I mean. Try something. Okay, that's it.
So are you actually programming the outcome of the?
Yeah.
Yeah.
Yeah, I mean, it's not very... It can be done by hand because there's so few graphs, but obviously I wouldn't do it by hand.
I might, because I can't program.
Yeah, okay. I mean, they're just graphs like...
No, that's fine.
You know,
oh, is it?
two edges, I mean, two parallel edges, another one back off.
So in general, there's a formula. I think it's your co-author, whose name just slipped my mind.
No,
No, Steve. Yeah, I think or maybe it was James and Dominic. But there's a formula for the Tut polynomial if you take the clique sum of two graphs.
Yes.
So there's no hope for using that formula, like for one. You've got to go take this more complicated approach, do you? Like,
that's a good question, actually. I mean, there are other. You mean there's other characterizations of series parallel based on?
oh no. Well, I was just thinking the general thing. If I give you a low order separation, so it depends which conjecture you're looking at. But I give you a low order separation in the graph, and then I describe the graph as the clique sum of two smaller graphs. By induction, something is true for the smaller graphs. Do you get anything by induction that way? I mean, it's clear that the induction is more complicated. I didn't fully understand what you're doing. I mean, it's also sort of like a dynamic program.
Yeah.
Yeah, and the other thing is, the question is that the obvious complementary question is, what happens if I give you some very, very highly connected graph drawn on a surface? What do you know about those graphs? Some genus.
Yeah, no, I don't know anything really. So, but I mean, pursuing via clique sums would be probably a sensible thing to look at.
Do you know what happens to grids?
Yeah, that's the other. I mean, if you can do low order sums and grids, it'd be interesting.
Grids are around the self-dual point.
Yeah, Carsten has looked at grids and found no counterexamples. So
Are they close to holding up quality though?
it's one of these horrible conjectures where whenever anything you can compute except the diagon, it easily holds. So you've got no clues as to sort of getting closer to something where it doesn't hold. It's like everything you try holds in states. So, but we should look at the clique sum idea though, because that would be a good thing to knock off. So.
How about delta y and y delta? We just want to go to planar graphs.
Steve and I have spent many happy hours trying to prove things for delta y and y delta.
You know the negative correlation stuff. With delta
Oh,
y
that's
graph.
right, yeah.
Oh my god. Now, how many times has people worked on that with delta y? Right.
Again, a good idea, but it just seems hopelessly slippery. You know, you just yeah. Okay, thank you, everyone.